Hello again and welcome again. In the last lesson, we were talking about reliable communication. And this was our last topic. That is a very efficient reliable communication protocol. It utilizes the bandwidth very optimal and it has a very good performance. But maybe if we are talking about real time, maybe we are going to have some problems. Let's remember why. What is the problem? Do you remember how it works? The transmitter can keep sending to a very high speed and sometimes it gets acknowledgements. And then it continues sending. But if one of these acknowledges report that one message is missing, then it has to roll back and send this whole message again and maybe continue from this position or maybe continue from the last sent messages. These are two ways how to implement this protocol. Let's see the most complex example. It keeps sending, but it has to store everything which is sending. Then it gets acknowledged, and then he says, okay, the receiver says, I got already 1, 2, and 3. And then he can remove from his sending buffer 1, 2, and 3, and then continue sending. And at this point, the receiver will say, okay, I got 4, 5, and 6. Then the sender can remove from his sending buffer 4, 5, and 6, and continue sending and storing. Then we lost the transmission of message number 9. Then the next acknowledge will report I got 7, 8, and 10. 7, 8, and 10. But 9 is missing. Then we have here the situation. It has to roll back up to now 9. Resend 9, and then maybe continue sending from the last position. From 14, then 15, 16, 17, and so on. It needs to resend only what is missing. Or the other way how to implement this, it rolls back to 9 and then it continues sending from this point again, 10, 11, and so on. And then we have the situation, this message was sent already and we are sending them again. So they are going to replicate it. In this case, the performance of the network will be a little bit lower because all these messages, actually we don't need to send them already, they were sent already and we send them back. But the opposite, you get nothing for free. Here, if you don't need to repeat from here, only resend the lost messages, then the receiver shall store all these messages, get the missing message, and then sort, because we want to keep the same sequence of messages, else we can have a very big problem. So it has to keep in a local memory messages 7, 8, then 10, 11, 12 up to here, then he got 9, then we sort, and now we can forward this group of messages to the user. Okay, and then we continue sending. As you can see, on the side of the receiver, we get messages with a very well-defined period. Then here, we are missing 1 messages. We cannot deliver to the final application message number 10. We have to wait until message number 9 arrives again. Then we have to sort, and then we can send very fast what we have in the buffer to the final application. Then the situation we are going to have, let me see, will be something like this. We are sending SAC with a defined period. Then we will have a very big gap until the message number 9 arrives. Then it arrives, we sort, and then we send very fast until we have sent to the application the last received message. So if we are talking about real time, the period of getting the message is not constant, and this could be a problem. On the other side, the sender has to make here a break and continue sending from here again. So it has to store. Okay. This is one problem if we are talking about real time. This is something which we shall analyze in order to know if we can use this protocol for our real-time application or not, depending how long do we have to wait until we forward the messages. And this is a function of the buffers, of the size of the buffer, how many messages we can store. Okay, then we have 2 buffers. One buffer here, what we call the sender window, and one buffer here, what we call the receiver window. And here, the sender window means how many messages do I have to store before I get the acknowledge for these messages. For example, if I have a window of 10, then I can send 10 messages and store up to 10 messages before I get the acknowledge for the last 10 messages. If I get no acknowledge, then I have to wait. I cannot continue sending. After a timeout, I have to resend again the last 10 messages which I have in the buffer. If I get the message, the acknowledge, then I can remove some the messages from this buffer and continue sending until I reach again the limit, the memory limit of my buffer for the sending window. On the other side, let me see, in this case, this shall be the window because I have to resend the number 9. So I shall not store much more than that because I shall be able to resend from 9 to 15. Okay, on the other side, we are getting these messages here, but from 10 to 14, I cannot deliver to the application. I have to wait until 9, then I can sort, and then I can forward to the application. This means how many messages the receiver can store in order to be able to sort before they are going to be forwarded to the application. Okay, and this is what we call the receiver window. Okay, then how it works? We have two windows. Let's say the definition, the transmitter window denotes the frames that have bit transmitter but remain unacknowledged. The transmitter must have enough buffer space to store the maximum number of possible number of unacknowledged frames. And then it has to wait until it has these acknowledges before it continues sending and refilling this buffer. On the other side, the receiver window, do you remember, on this side, denotes the frames that can be expected to be received out of order. If we have a window of size 1, this means all frames which we get, they have to be in the correct sequence. We don't have any buffer to store messages from the future and then sort and then forward. So all messages which we get have to be ordered. And a larger window, larger than 1, this allows the receiver to receive as many frames as we said here in order to sort and then to forward to the final application. Okay, the receiver must have enough buffer space to store the maximum number of frames that can be received out of order before sorting. Okay, then we have two windows. And we have to agree, both sender and receiver has to implement a communication protocol before to set up a communication and say, please reserve so many buffers for my messages, and I'm going to reserve so many buffers for my messages. And so is how it works. First, we have the negotiations about the window size. The sender will say the receiver how the size of its windows, and then the receiver knows how long it can wait before it sends the acknowledgements. So if this sending windows is very short, for example 1, then we have this situation. Not very efficient, because after every message we have to send a message, we have to send an acknowledge, and then it can continue. If we have a very big buffer here, then it can wait to receive as many messages as he has in sending window, and then he sent a merge one big message with all acknowledgements for all these messages, so it can be much more efficient. Okay, and on the other side, the receiver will say what is the size of his receiver window, and this means how many messages he can send out of order. For example, if he cannot send any message out of order and the message 9 is lost, even if it has sent already up to message number 14, it had to repeat from message number 9 to the end. And he knows he has a message window, a receiver message windows of 3, then maybe he has sent up to 14. But he knows, okay, I have to resend 9, but 10, 11, and 12, I don't need to resend them again. They are already in the receiver buffer. So these 3 messages will be sent only once. I don't need to repeat. And this is the efficiency. If the windows are bigger, then the efficiency of data transmission will be higher. Real time is another topic. Okay, this is first in negotiations to set up the size of windows and how often do I have to send the acknowledgements. And then we transmit. For example, here we have a window size of 3, then we can transmit 3 messages, and then it will send the acknowledge, please continue from 4. And then I will send again 3 messages, and then it will send an acknowledge, please continue from 7. Okay, and so it's how it works. First, we build this synchronization, we build a communication channel. So I said, I want to communicate with you, and this is my set window. My puffer, my number of puffer, my sending window. Then it will acknowledge, okay, I accept your communication, and this is the size of my window. So both know already what is the size of the window of the other side, and this is a limitation how many messages we can send before we receive the acknowledges. And then we make the transmission, as said before, so many transmissions and acknowledge, so fill transmissions, so many transmissions and acknowledge again. And at the end, we have this finalize and close the communication. And this finalize and close the communication is required in order to set free the allocated buffer. So at the beginning, when we negotiate the size of the buffer, we have to allocate as much memory as we need for sending and receiving windows. And at the end, when the communication is closed, then we can release these buffers for other communication channels. Okay, and this is, as I said before, in terms of reliability, a very good protocol, but in terms of real time, maybe. Okay. Up to now, we were talking about reliable communication, and those are the upper layers. We have another parameter, and this is the medium access. How much time do we have to wait until we can send our messages? But let's compare. If we see the effort or the time delays and jitter we introduce here, and the jitter and delays we introduce here, we have a situation like this. For reliability, with the upper layers, we will have introduce a delay and jitter of this size. And for the medium access, we will have a jitter or delay of this size. So if we have here a lot of delays due to reliability, then what shall we care about small delays due to access protocol? But in case we have a real-time protocol with no reliability, we are just sending, then we will have here almost 0, and then we shall really consider the delays here for the access protocol. Okay, we have this situation with access protocol. Let's talk about the lower layers. We are talking almost hardware now. The upper layers, there was software, how to implement acknowledgements and so on, and all this, with the exception of the low-level acknowledge. With this, a low-level flow control with the stop and continue. This could be implemented in this hardware layer. But all other implementation of buffering and so on, these are upper layers, software layers. Okay, let's talk about this. First, we have a medium access protocol. And this is when can we access the medium in order to send. We have these two situations. For example, if we have point-to-point connections, then the sender is the owner of this link, of this medium, so there is no access collisions. It can just take and speak whenever he wants. It's his own link. But another situation is something like this. If we have a broadcast medium where many nodes can send at the same time. This is the case, for example, for a wire, a communication bus, or maybe a radio communication. Then we have a common medium, and then we have to think how to access this medium to avoid collisions. We could say, okay, let's try. If we have collisions, we try again. This protocol exists too. But now, if we want to access collisions free, then we have 3 methods, which I'm going to show you now. First, let's say, what is a collision? For example, if we have a common medium and two try to send data in the same medium at the same time, then the data will be overlapped. We have a collision, and the receiver will get only noise, only trash. It will not be able to differentiate which message is coming from there and which message is coming from there, and they are two messages, but if you're the receiver, it's only noise. So we have to make some kind of order to say, okay, first talk you, then you, then you, then you. Like in a room, like in a room, if everybody is talking at the same time, you will get only noise. It's better if first then, and so on. And this is one type of time access protocol to divide the time which you have in different slots. So one is to communicate after the other. But that's not the only way. We have to access the channel and avoid collisions. Let's see the three common examples, the common ways we have. Okay. What I said before is the time division multiple access. We have here two parameters. We have the time and we have the frequency. For example, radio modulation. Let's see an example. Maybe this is prior to your time, but it was a time where you have an auto radio or an radio and you could select the frequency to hear different channels of communication. Okay, this is this frequency medium. So if you have different times to access the medium, so you get access to this, then you can use all frequencies. The wire is yours now. And then you can send all frequencies and send as fast as possible. The other way is to divide the medium in different frequencies, like the radio, which I said before. In this case, you don't have to wait. Each sender will have its own frequency, and it can send all time, but only access this small bandwidth of its assigned frequency. Here, every sender can use all frequencies at the same time, but it has to wait until the time is allowed. So for his time slot. Okay, and this is what we call frequency division multiple access. And a very clever solution is the code division multiple access. So all senders can send all time and use all frequency, but to be able to differentiate who is talking and to be able to separate different messages, we modulate the data on data. And that is a very clever solution. Let's see this diagram, how it works. The time division, so you have a time cyclus, and then first you get sender 1, sender 2, sender 3, sender 5, and then again sender 1, 2, 3, 4, and 5. So every sender will get a time slot. With frequency, I said before, every sender can send all time, but it will have a small frequency slot. So the bandwidth will be less because the frequency has to be split in different senders. And here the bandwidth will be less. Every sender can use all bandwidth, but not all time. And here we have something like this. We have a code modulation. So every sender will transmit always a defined bit pattern, two defined bit pattern, one defined bit pattern to say it's a 1, and another, the inverted from this, to say it's a 0. So you can have a correlator, and this correlator will search for this bit pattern between all noise, because all are overlapped. All these frequencies on all senders are overlapping. But this code which is sending is a special code for everyone. So if you have a correlator which is looking only for this bit pattern, then it will recognize the bit pattern is there or the bit pattern is not there. And so you can recognize 0, 1, 0, 1 from each sender. Okay, but even if you can send all time and use all frequency, the bandwidth is not so high because you have to modulate your data. This is the data on the top of this pattern. And the size of this pattern depends on the amount of channels you would like to share. Okay, we are going to concentrate on this time access protocol because this is what the most simple and most reliable for real-time communications. Okay, now let's see, we have this access, we have different computers, and we have this network, a common access. What shall we do? We have different ways to access the medium. This is the tree for the access methods. Okay, we have a controlled access, or we have competitive access. Just try and try until you are able to get the message. From this competitive access, we have two ways. Collision happens, so you try, maybe there is a collision, then you have to try again. Or a collision free, which is a very clever idea from the CAN bus, which I'm going to explain later. Or we have a access control, and we divide the time when everybody is going to talk. We can have it decentralized, every know when it shall talk, or we have a central unit who says now you talk, now you, and now you. Let's go one after the other. If we are talking about real-time applications, then we have to have a defined time access. And all these are very well for real-time communication. This, when collisions happens, it says no guarantee how long you have to wait until you have access to the medium, because you try, if there is a collision, stop, try again, stop, try again, and so, and it's not bounded. So there is no limit. The probability you will have to try 10 times or many times before you have access are decreasing, they are very low, but there is no guarantee. So there is no bounded limit how long it will take until you have access. With all this, there is a bounding limit, so they can be used for real-time communication. Okay, now let's see more details of each of these cases or methods. Let's begin with collision happens. So we have what we call carrier sense multiplexes with collision detection. Carrier sense, this means you are hearing. You are not only talking, you are sending, but you are hearing the content of the medium. So if you are sending some data and you are hearing and recognize the data in the medium is different than the data you are sending, then we have a collision. Or you can first hear the medium, it is free. If it is free, you can begin sending. If not, then you have to wait until it is free, then you can get access. And this is carrier sense. Multiple access because several can access, and collision detection because you can recognize if the data is being corrupted. For example, if two are sending at the same time, if they are sending exactly the same data, there is no problem. There will be no collision. But if you are sending one on the other is sending 0, then will be a collision, and the network will have, or not the network, the wire will have noise. So you will recognize I'm sending data, but I am reading noise. It's not 0, it's not 1, there is a collision. And then you know I have lost this package. And the other has lost this his package too. And so is how it works. Okay? As I said before, carrier sense, multiple access, and collision detection protocol. Any device can try to send at any time. So there is no time slot. When you want to send, just try. Not just try. First, see if the network is the wire is free. Each device sends where the lines and therefore are free, and therefore the network is available. So first here, if it is clear, send. If not, wait until he concludes, the other concludes, and then you can send the data. Okay, if no one is sending, you can begin transmitting. If two or more devices try to send at the same time, then we have a collision. I said before, when you are going to hear, you are going to detect noise. Not your data, but noise. Then the frames are discarded. Both sender had lost his message because now there is only noise there. Both stop sending now, and then each one will wait a random time and try again. If they will wait exactly the same time, then we'll be keeping in the same collision once and once and once, and this will have no end. Therefore, we have to wait for a random time. So there is a collision. I will wait 2 seconds, the other wait is going to 3 seconds, then one is going to come first, the other one is going to recognize there is someone sending, then I have to wait, and it will work pretty well. But it is possible they are going to have the same random number, or when you try to send, someone else is going to try send, and then you have again a collision. And then you have to repeat this procedure again and again and again. Therefore, we say we cannot guarantee how often you have to test, to try, before you can send your message. The probability of many collisions after another is very low. So the probability of 2 collisions is very low. The probability of 3 collisions or 4 collisions almost 0. But there is no guarantee. It could occur. And if you have time critical data, then you are lost. Okay, and this is what we use in Ethernet. That is the typical implementation of Ethernet, is an stochastic access. It cannot provide a non-upper bound for transmission time. So, therefore, normal Ethernet is not suitable for real-time applications. But there are other versions of Ethernet, for example, the time-trigger Ethernet, which works pretty well. I'm going to talk to this about this later. Now, a more clever solution is, for example, the CAN bus. It's carrier sense, like before, so they are hearing what I sense, but they detect and avoid collisions. And I'm going to show you how it works. So, we have binary data, and we can say electrically the 0 has priority. It's like a pull-down switch. And a pull-down switch looks like this. You can send only zeros. You cannot send a 1. If you send something a 0, then you close this switch. This is actually not a switch, it's a transistor. And then you connect the bus to ground. And then a bus in ground is detected as a 0. If you let this open, then this resistor will pull slowly the voltage here to high. And then you will have a 1. So if you want to have a 1, send a 1, just do nothing. It will be a 1. If you want to have a 0, then close the switch and it will go to 0. And now let's see what occurs if 2 are sending at the same time. So if they are sending the same data, then there is no problem. It will be exactly the same. If one is sending a 1, so it will keep this open. The other one is sending a 0, then it will close this. Then the bus, this line, will be pulled down to 0, and then you will detect clear a 0. So you don't lose this bit, you don't lose this message, but it's clear a 0, and the other one says, okay, what I am sending, it's not there, someone else has priority. Okay, and so work. Let's assume we have 3 nodes, 1, 2, and 3, and this is the bus label. That is what we find here. And these 3, each one has something like this. Okay, at the beginning, they are sending exactly the same data. Then there is no collision, it can continue, we can continue. So at this point, all of them are sending a 0, a 1, perfect. But then, in the next situation, this is going to send a 0, this is going to send a 1, this is going to send a 0 too. And then, what we will find in the line is a 0. So, he says, I am writing 0, I find 0, everything perfect. This one says 2, I am writing 0, I can see a 0, then everything perfect. But this will see, I am trying to write a 1. But what I see here in the bus is a 0. So I know someone else with higher priority is sending now. So I stop sending. And then this will stop sending, wait until the end, I try again. So the one with the most zeros there has the higher priority. And at the beginning, we have an identifier of the message. And the identifier is something like the priority. The identifier with most number of zeros has the highest priority and will be able to transmit the data. The other has to wait until the bus is free again. So using this very clever method with priorities, we avoid collisions and we are not going to lose data if 2 are trying to send at the same time. Okay, let's continue. At this point, node 1 and node 2 and node 3 find their data in the bus, so we can continue. Then the next, they send both 1, 1, perfect, no problem. And here we have a difference too. This send a 1 and this tries to send, this send a 0 and this tries to send a 1. And this will recognize, oops, I am trying to write a 1 and I find a 0, then I have to let the bus, I stop transmitting. And this, he will see, the bus has exactly what I am sending, I can continue. And then it will continue with his data. And so there is no external arbiter. It is, just a second. Okay. And the bus, the access to the bus is self-regulated. A very clever idea. And this is used for many real-time control systems, especially in cars. Okay. The next will be this decentralized time trigger protocol. But I'm going to talk to this at the end because this will take the longest time because this is the emphasis of this presentation. Okay, then let's talk about a centralized access control. So we have to create time slots and someone is going to say who is going to send. That is a central arbiter. And it works like this. We have different nodes which would like to access the medium. This is not the medium, this is just the request. And everyone can send a request to the arbiter, and the arbiter knows if someone is using the bus or not, and then it will take the decision who may access the bus or who may access the medium. And this is the grant. So if only one is making the request, I would like to say, then there is no problem. He can say the grant and say, yes, please, you can talk. And when he concludes, then he removes his request, and then the arbiter will know now is the bus free. The arbiter doesn't need to hear the bus. He looks only this request. And a request shall stay active from the beginning until the end of the transmission. So he knows if the bus is used. Okay, let's assume now this device is sending, but this device will like to send too. Then it makes a request and the arbiter will see someone is talking, so please wait. So it will not send this grant. When this concludes, then it will send this grant and this will continue, can begin writing. And this will keep the request until it concludes. And then the arbiter will know someone else can continue. Well, that is a centralized arbiter. We can have a decentralized arbiter with priorities. For example, here we have again 3 devices, and each one can make a request to this line. And if it makes the request, this has the higher priority, it will get the bus. He can transmit. Now let's assume he wants to communicate too, then he makes this request, and if he gets access depends on if someone else is working with higher priority and if he is making the request. So to get this grant, this request has to be set and this shall not be set. So no one else with higher priority is using the bus. And the last one with a lower priority is to get access to the bus. First, he has to have a request. This may not be active, and the second one may not be active. So it will get access only if he wants, and the ones with higher priority doesn't want to access the bus. Okay, and this is a distributed arbiter. Or we can use something like a talking passing. So there is a request, everybody is doing the request, and if the request line is set, then the arbiter says, please do. I don't know who, but do. And we have here a chain. He will get, you may, but he will say, if I am making the request, then I am taking the bus. If not, I'm going just to pass the signal to the next. And the next will do the same. He will say, I shall access the bus, but I am not making a request, so I'm not going to use this. I pass to the next. And the next will see, I am requesting the bus, and I got the grant, then I can access the bus. And maybe he would like to access the bus too. So he has set this signal too, but this is not going to be forwarded until this concludes. So he will not get no access to the bus. Then this has concluded, and then he says, okay, I can forward this grant to the next, and the next, which is waiting, will get this grant and will get access to the bus. Okay, this is how we can have a centralized access to the medium or to the bus using an arbiter. With the arbiter can be central or can be distributed, like in these 2 cases. Most of the time we use a central arbiter, which can be more intelligent, have priorities or take into account how long each request has been waiting. Okay, and now for us the most important topic, the decentralized time trigger protocol. We are going to talk a long time about this because this is most time of use very often. Okay, this is a time division multiplexes. I said before, the time will be partitioned in slots, and every device, every sender will get a slot. Okay, is access to the communication medium by temporal rules. These are the time slots when everybody is going to send. These time slots are stored decentral in each node. So each node knows when it shall send. It's important. We have to have a synchronized clock. And this is used in, for example, time trigger Ethernet, say bus, and other time critical communication mediums. Okay, now let's see these time trigger protocols. Okay, these time trigger protocols are used, for example, for time trigger Ethernet, time trigger radio links, time trigger bus, and time trigger, etc., etc. They are used in many different configurations. And this is most suitable for applications with regular data flow. Do you remember at the beginning of these lessons we saw there are regular data flows, for example, what we need in control systems, or we have data streams which the size of the messages, of the frequency of the messages is not defined. This is not important for this case. In this case, we need these regular data flows where the size of the message is constant and the frequency of the messages is constant too. So let's say a constant rate. For other, for example, CAN protocol is good for this dynamic scheduling using priorities where we don't have this constant frequency or constant size of the messages. Okay, and now let's say how this time divisions multiplexes works. Something very important, it's controlled by time. So all participants have to have the same time. And therefore here, time synchronization is a very important issue. If one of them is going out of the time synchronization, then we are going to have collisions and the communication is not going to work. Okay, on how it works, the total channel bus capacity is statically divided into a number of slots. So from the beginning, normally it's not dynamic from the beginning. You know how many senders you have, and you assign for each sender a time slot when it shall send. And this periodically, it will be repeated. Okay, I said before, each slot is assigned to a certain node, a processor. In a system with n processors, the sequence of n slot is called the TMA round. So first then, and then we repeat. That is the cyclos. And the frames, just a second, and something very important. Each processor shall send. It gets its time slot and it shall send to keep the system synchronized. Even if it has no data, then it shall send no data, but it shall send something. Else, if there are very big gaps, then we can run out of synchronization in the whole synchronization bus. So even if no data has to be sent, you have to send a message which says, I have nothing to say. Okay, and this is something like this. We have the cycle, and then this is the slot. And these are the different nodes which are going to send. And then the next cycle, again the same. And if we have a failure here, then we know after 1, I shall get data from 2, but I got no data from 2. Then after the timeout, 3 may send. And everybody will know 2 have failed. So let's wait a timeout. If the next time I get data from 2, then it's okay. If the next time 2 or 3 times I get no data from 2 in this example, then we know this node has failed, and then we have to perform a recovery action. Because I said before, every node must send when it gets its time slot. And now we shall know when every node knows when it shall send, according to the time. He knows at what time it shall send, the size of the period, and which is his position in this period, and send again. Therefore, the time synchronization is very important. If the size synchronization fails, then the whole system will not work. Therefore, the global time valid through the whole system is very important. And design synchronization can be a very complex mechanism, but it shall be done before we begin with this communication. But we don't need the exact clock of every node to be synchronized, but what we call the macro ticks. Okay, how it works. The time is counted by an oscillator. So we get a clock, and then we have a time divider. We count how many pulses we have had, and this is our notion of time, this clock divider. And it works like this. We have to make a difference between what we call the micro ticks and the macro ticks. The micro ticks is the frequency of the clock, of the local clock of the computer. For example, let's assume here I have a very high frequency. This has a factor of 1. Then I can have a binary divider. Then I can divide this frequency by 2, half frequency, a fourth, an eighth, and 64th frequency. And so I can divide the frequency in steps of 2. Or I can have a comparator, and I can divide by any number, not a binary counting, but I can divide by 3. I can generate a pulse every 3 cycles, or by 4. I can generate a pulse every 4 cycles, by 6, by 7, it doesn't matter. And this is what we call the macro ticks. We have to make a division, time division of this high frequency to a lower frequency. The frequency which we are going to use for communication, it has of course to be lower than the clock frequency of the CPU, else it will be really difficult to implement. But in the system, we have to have a synchronized clock, a synchronized time, but not the micro ticks. The micro ticks are not important for the communication. What we need to synchronize are the macro ticks. And something important, maybe different processors will have a different frequency, so it doesn't matter. But the macro ticks have to be the same for all nodes in all systems. So this divider is a function of the frequency of each clock, and it can be from node to node or from device to device different. Okay, a definition of this time progression. All nodes have to have the same macro tick duration in each node. Not the micro ticks, the micro tick may be different. Don't forget this. And they have to have the same point counter value. So they have to begin at 0 at the same point. So they will know when is their time point to synchronize. And this 0 doesn't have to be the booting of the whole system. It can be, for example, the beginning of a communication period. And start counting as close as possible. So we have to have a synchronization. So all nodes will begin with the counting of this time to know where is the slot, hopefully at the same time. And then we shall try to keep all clocks as close as possible to each other. Okay, and this is what we have. We have the micro ticks, which are important only for the CPU, for the internal processor. Then we have the macro ticks, which shall be synchronized between all computer or all devices. Then we have the slots, and a slot is a number of micro ticks. So we can say this typical slot will have 1,000 micro ticks, maybe 1,000 bytes or something like this, or bits, but it's a function of micro ticks. And then we have a cycle. In this cycle, we repeat all these slots. So in this cycle, we have merged slots. If we go back to this diagram, just a second, this is our cycle, which includes more than several slots. This is one slot, and this slot has several micro ticks, and the micro ticks consist of many micro ticks, but this is for the word communication not important. And now we have the situation, different clocks maybe differ. We have maybe that is the reference clock or the real-time clock, and then we have, for example, here a bad precision with good accuracy of different clocks, so they are drifting, but they are not very far away from the real clock. And in this case, we have a good precision because they are not drifting so far away from each other, but bad accuracy because they are far away from the reference clock. But this is for us a problem, because important for us is not the global clock, but is the shift between different clocks of the communication system. So for us, it's more important that our clocks are differing in the same direction and together and have the same speed, even if they are far away from the reference clock. This is not very important for us. Okay, the time trigger communication. Let's see some examples. We have different nodes here represented by different colors, and then we have the major cycle. In this major cycle, all nodes shall get at least one slot to send its data. So begin from node 1 to node 6 and then begin again. And this is, all nodes are the same, all nodes have the same requirements of data to be transmitted. A little bit more complex is, for example, nodes might differ. Some nodes might require more bandwidth, more communication than others. For example, the green one requires to send data every 25 milliseconds. The yellow one requires every 50 milliseconds, and the red one requires every 100 milliseconds. So we have to create a major cycle where everything will be repeated on a minor cycle which can be different from minor cycle to minor cycle. So let's say we divide, we see the lowest frequency over is 25 milliseconds. So the minor cycle shall be 25 milliseconds. And the biggest one is 100 milliseconds, so we are going to repeat everything all 100 milliseconds. So we make in the minor cycle, the red and the blue shall transmit every 25 milliseconds, so they are present in every minor cycle. But this, the yellow, needs only to be in every second minor cycle. So in the first one, it's not here, we transmit here, and 50 milliseconds later, and then 50 milliseconds later. And this one, only once per 100 milliseconds, so it will be here, for example, in this minor cycle, and again in the next cycle. So we have divided our communication slots in major cycles, which are going to be repeated and are exactly the same, and minor cycles, which may differ from minor cycle to minor cycle. So we can assign to different nodes different number of slots. Another possibility will be in one major cycle to have different slots for every node, but it makes everything more complex, more difficult. We have another possibility. Maybe we have different messages inside of each node, and the messages have different frequencies. But let's say each node will get this slot very periodically, but not in every slot I have to send all messages. For example, when I get my first slot in this period, I send message 1, 2, and 3. And then all other nodes will get their time. Then I get the time again, I get my slot, and I have to send the message 1 for every slot. Then I'm going to send, and then 2 and 3, not necessary, but I can send message 6 and message 8. And then I get a slot again, and then I can send message 1 and message 2, and so on. So internally, every node can organize which message to send in every node. Important is I have a maximum length of the slot. I have to count the size of all messages what I shall send, and be aware of do not go beyond the end of my slot. And another important thing, I said before, even if I have nothing to send, I have to send some data in every slot. Else, all other nodes will think I have failed. Okay. And another method is to have a synchronized schedule at the end of every major cycle. So I have a major cycle, and in the beginning of the major cycle, I send the schedule when each node shall send. And then this schedule may be dynamic, configurable, and then I will send, okay, just a second. Yes, I send which node shall send one, at what time, and something important. This time point where I am sending the schedule, that is the synchronization point. At this point, all senders had to set their clock to 0, and then they begin counting the time from here until the end of the cycle, until I send the new schedule. Then at this point, all nodes will synchronize their clock again. The nice thing here is the period of time between synchronization of clocks is very short, only the length of the period, and therefore the drift from clock to clock will be minimal. And now let's see the summary of TDMA. This is a very important topic because this is very often used in control system, in real-time control system. Okay. As summary, I can say the TDMA particular means a statical partitioning of access of the medium, timings, and it's static. And each process knows in advance when and how long it might send. Also, he knows its load when it shall send. And the collisions are avoided as processor knows the time point where they might access the medium. If the time drift, then we have collisions, and then we have a very big problem because the protocol has no means to handle these collisions. And the message passing is bounded, so there is a maximal limit of the time duration. Okay, and if we have messages which are longer than my slot, then I have to split this message in frames. So these frames can be fixed in one of these slots which I have, but I may not send longer than my slot. And not all slots from different nodes have the same length. Some nodes have a lot of data to transmit, and some nodes have very low data to transmit, so the length of the slot might be different from computer to computer. But the slot length is a constant for every computer. So in every cycle, we will repeat exactly the same procedure like the cycle before. And the length and of the cycle, the sequence and the length of each node, it's set by designer. So the programmer has to define this parameter, and it is not done by a scheduler, and it is not done in real time. And the advantages of this TDMA is it has a high degree of predictability. We know when the data will when the data transfer will take place, and it's very well suited for safety critical applications, real-time applications. The problems here is it can lead to a poor utilization of the available bandwidth. For example, if nodes had nothing to say, they have to send. So they are consuming empty slots. They have to send. And there is a low degree of flexibility. From the beginning, we know which nodes are there and when they shall send. We cannot add nodes dynamically, or we cannot remove nodes dynamically. It's a static protocol, or protocol definition of the access protocol. Okay, thank you very much.